Hi, my name is Prajesh Prasad from the Interdisciplinary Program in Educational Technology at IIT Bombay, India, and I will be presenting our paper, How do Graduating Students Evaluate Software Design Diagrams? So when graduating students enter the software industry, they usually start working on existing large and complex systems, and their typical tasks involve resolving bugs and writing additional features based on new requirements. And these activities require them to explicitly understand and evaluate a given design. So, what do we mean by software design evaluation? Let us take the example of an ATM system. The requirements for this ATM system are that a user with a valid account can register and set a PIN. The PIN should be of certain length and should maybe contain only numbers. When the user enters the ATM card and inputs the correct PIN, they are given options to withdraw and maybe change their PIN. And if the balance is less than a certain amount, the withdrawal should be denied. Now, for these requirements, the design can be created using UML diagrams such as class and sequence diagrams. In order to characterize software design evaluation, we have used Linlan et al.'s framework for software quality. According to Linlan et al., software design can be evaluated based on three categories: syntax, semantics, and pragmatics. By syntactic quality, we refer to how well the model corresponds to the rules of the language. In this case, the rules of the language are the rules of UML diagrams. By semantic quality, we mean how well the model corresponds to the requirements. In other words, are all the requirements being correctly mapped to the UML diagrams, and is there something in the UML diagrams which is not there in the requirements? And thirdly, by pragmatics, we mean how well the model corresponds to its audience interpretation. For example, is the UML diagrams readable? Is it easy to understand? And so on. We have restricted our focus to semantic quality, and by that we mean given a set of goals and requirements and a software system design, does the design fully satisfy all these goals and requirements? So for example, certain semantic defects in the ATM example could be that the minimum balance requirement is not checked during withdrawal, or there is no check if the withdrawal amount is greater than the balance. When we look at literature for strategies for evaluating designs, we see that experts, they create more detailed mental models of the system and perform mental simulations on these models. They also employ various reasoning techniques like simulating scenarios in the given problem. We have also looked at literature from empirical software engineering, and we see that there are various studies which focus on reading comprehension and maintainability of UML diagrams. For example, studies which look at which diagrams lead to better diagram comprehension, the effectiveness of different forms of notation, and the effects of UML diagrams along with source code. We also see that experts, they rapidly switch between different diagrams in order to create an integrated model of the design. They also employ various cognitive processes such as perceptual processes, which is a bottom-up activity of sensing something and knowing its meaning and value, and conceptual processes, which is a top-down activity in which they generate, refine, and validate hypotheses based on the provided design diagrams. So this forms the basis of our study, in which we try to answer this research question of how do graduating students evaluate software design diagrams against the given requirements. We conducted the study with 100 final year computing students, and all of them were familiar with class and sequence diagrams, as they were introduced to these diagrams in the previous semester. Student was provided with one class diagram and three sequence diagrams for an ATM system, and their task was to identify defects based on the requirements and for each defect they had to provide a logical explanation of why they thought it was a defect. So the requirements for the ATM system was given to them, and certain semantic defects were introduced in the design diagrams. For example, there was no check to see if the user is already registered, the PIN requirements were not checked, the minimum balance requirement also was not checked during withdrawal. Moving on to the data sources and analysis, our primary data source was student response sheets, and we used an interpretive content analysis in order to analyze the student response sheets. So in the data analysis, we typed each of the student responses into a spreadsheet. The unit of analysis was a sentence or a group of sentences which referred to a particular defect. We then generated descriptive codes for each of these sentences, each of these responses. So the objective of descriptive coding is to avoid any bias or preconceived notions but stay close to the data. Then for each of these codes we generated categories and subcategories, and finally we generated broad themes from these categories. Moving on to the results, we see that from the student responses, students focused on the semantic elements in the design. They identified necessary scenarios which do not satisfy the requirements, and they also identified necessary functions which are not used. For example, check minimum balance and update balance functions are not called, and students correctly identified that these were missing in the design. There were some students who focused on syntactic elements in the design as well. For example, change in data types, functions of class diagram. So some students incorrectly mentioned that the data type of the account number or PIN should be int and not string. Then the third category of responses which we got was students focused on adding new elements into the design. For example, they focused on changing existing functionalities and requirements and adding new functionalities such as forgot PIN, two-step authentication, language preferences, and so on. Adding new functionalities are not wrong in itself. In fact, many of these functionalities are essential for an ATM system. However, the focus of the task was to evaluate the design diagrams against the given requirements. Hence, adding new functionalities was not the goal. This pie chart shows the percentage of the different types of responses. We see that there were around 11% of responses which added new functionalities, and around 22% of responses in which students changed the existing functionalities and requirements. So why do students focus on syntactic defects alone? We believe this question can be answered by conducting qualitative studies with students, but we hypothesize that this is due to the mental model which students create based on the requirements and the design diagrams. In their mental model, they restrict their focus to just a surface level comprehension of the design diagrams, and hence they are able to identify only certain syntactic defects. Then why do students add new functionalities? We believe this is due to the prior knowledge of the problem space in students' mind. So the ATM system is a familiar problem to them, and the problem domain model is already available in the student's mental model. And hence they form hypotheses about their expectations of the design based on their experiences. And when they observe that there is a mismatch between their hypothesis and what is present in the design diagrams, they flag these as defects, and hence they add new functionalities into the design. Students may find it easier to simulate scenarios pertaining to these new functionalities rather than deeply explore the design to identify semantic deficiencies. Moving on to the limitations, we have restricted our scope to focusing on the semantic quality of these design diagrams Uh, our scope of design diagrams are just restricted to class and sequence diagrams because we believe that these are the diagrams which students are exposed to and the most commonly used design diagrams. And there are differences in prior knowledge and experience in students which might have affected the results of the study. Moving on to the implications, we believe that the results of this study has implications for instructors as well as computing education researchers. For instructors, it provides them insights on what students think of when asked to evaluate design diagrams. They can also develop interventions to address student difficulties such as creating new requirements and failing to identify omitted requirements and so on. Computing education researchers can conduct similar studies in which they focus on other characteristics of evaluation, maybe different diagrams of different complexity, and also conduct other qualitative studies which could help them uncover what students are thinking when they are asked to evaluate design diagrams. Here are certain points which we can discuss during the discussion time. Firstly, this behavior of students adding new functionalities to the design. So this has been a surprising finding for us. So why are students adding such functionalities? What other alternate explanations are possible? And are there parallels with the programming literature as well? And what type of interventions can help us address these difficulties? And finally, what additional studies can be done to investigate students' behaviors while they evaluate design diagrams? Thank you for listening.